Yes. So, in the previous class we were discussing about sigmatropic reactions, right. So, we broadly classify sigmatropic reactions as 1N and as well as NM sigmatropic reactions. 1N, we said that the residue will move from the first position to the nth position, and NM rearrangement we focus like it will be the movement of your sigma bond across your pi system. Then in 1N system we again broadly classify that as hydrogen movement system and carbon migration system. So, we were dealing about hydrogen shift. So, what we studied there, we studied like reactions like 1,3, 1,5 and 1,7, and then we slowly got into their stereochemistry. So, stereochemistry mein we studied two things, right. One, it should be suprafacial or it can be intrafacial. Then we add this Woodward-Hoffmann rule for your 1N hydrogen shift. So, we said that we will take 4N plus 2. I am talking about the number of electrons involved, it will be pi system as well as sigma electrons. Then I said heating, and in the light we said it will be intrafacial and will be suprafacial, and just it will be opposite to this. So, what I mean is that if I take 1,5 system, okay, 1,5 hydrogen system, so it will be 6 electron systems. So, 6 electron system, if I heat it, I might end up with a suprafacial, and on the light it will be intrafacial. And if it is a 1,7 system, it will be other way around. But there was one thing you have to remember, which is that 1,3 shift. Okay. In 1,3, normally you do not observe any type of reactions on heating. Yeah, when it is light, then you can see suprafacial, but on heating you do not see the any type of reactions, you do not see 1,3 hydrogen shift. We will just see why it is. Okay. R prime, better to write it so that I have a system like this, which is an with an hydrogen. Now, if I heat this, what happens? So, by theoretically I should expect a 1,3 hydrogen shift, right. So, if you feel this how this reaction goes, just for an assumption that the bond cleaves here, okay, we think like it goes by a sort of radical. Okay, it is not completely, because it pericyclic goes by transition state. Okay. If you, for assumption, if you feel that reaction goes like this way, like get an cation, then you can write as H plus. No? This can give you the product. If you feel this goes. Now, so I am dealing with this system. Okay. This is what? This is an allylic cation, right. So, we are concerning about the heat. So, what we have to, which orbital we will be looking into it? We will be looking into the HOMO of allylic cation, right. Just we draw the HOMO of allylic cation, how it looks like. One way of writing it in a proper way is that you have an R, R prime. Okay. That's my hydrogen. Okay. So, this is my allylic cation which I have taken the HOMO of it, okay, 1 3, and this is my hydrogen. Okay. Now, if you see this reaction, what happens? It has to go, and if I has to shift, it has to shift like this, but if you see, it is orbitally not favored, right. So, suprafacially it cannot do the process, because it is orbitally not favored. That is the rule. Again, the rule, if you put this in that Woodward-Hoffmann rule, it says yes, it should not be a suprafacial, right. That also matches with your orbital 1. Okay. Now, what I do is that same system, so this is your hydrogen. So, what the rule says? The rule says it can be intrafacial. So, it can do an inversion to come here. Okay. So, your hydrogen can do, but this is if you see orbitally it is favored, but what happens, your hydrogen is very small. Okay. It cannot bind, it cannot do this binding because it is very small. That is why intrafacially also does not occur. Even it is orbitally favored, you can say geometrically it is unfavored. Because hydrogen is very small, so it cannot bridge between this two orbitals. That is the only one exception which comes for this rule. Otherwise, it just everything fits to that rule. Okay, 1 3 1 5 1 7 all this fit exactly. Only in 1 3 if you go for your heating, both suprafacial and intrafacial does not occur. See, if you see the same system photochemically, so what happens in light? So, in light I will be taking the LUMO of I will be considering the LUMO of allylic cation. So, how to draw the LUMO then? So, this will be the LUMO of your allylic cation. You have your hydrogen, fine. Now, in light it can easily do this, it can move suprafacially, because you see orbitally it is favored, it can just move from this to this and suprafacially, fine. So, same thing you can do for your 1 5 1 7 everything. So, this is orbitally favored as well as geometrically favored. So, the reaction happens nice. Okay. So, that is what 1 3 1 5 and 1 7. Only one thing to remember, 1 3 Normally people ask this question all the time, yeah, why 1,3 does not happen on heating. Okay. The reason is that 1,3 by if you heat it geometrically, it is not favored, because the hydrogen nucleus is very small to make a bridge between this. This point you have to remember. Okay. Fine. So, that is about your 1n hydrogen shift. Okay. So, now we will move to your 1n carbon shift. If methyl moves, then you say it is a methyl shift. Okay. We will start with the simple example. Eat this. So, you get a, so this will be 1, 2 and 3. You have a nice methyl. Okay. So, you can call this as 1, 3, right, because it moved from 1 to third position. So, you call it as 1, 3, and here you can call them as methyl shift, 1, 3 methyl shift. Fine. So, same way you can draw for your 1, 5 and 1, 7 as you did for your hydrogen shift. Now, then comes your stereochemistry into question, whether this will be suprafacial or it will be intrafacial. See, if you just take a methyl system, okay, then what happens, you can write the same rule for your Woodward-Hoffmann, like I can write just like your hydrogen shift. This also obeys your similar like your hydrogen shift. Initially it will be intrafacial 4n, then it will be supra 4n plus 2, just reverse of it. So, just similar to a hydrogen shift when it is methyl. Okay. Keep that in mind, when it is methyl. Any doubt up to this? Okay. See, the one interesting aspect comes in this carbon shift, that is that, for example, I have a system. Okay, I have a system like this. Now, what happens? Your carbon is sort of chiral. Okay, I am taking as carbon. Previously, I said it is only a methyl shift where your carbon has 3 hydrogens. Now, I am slowly introducing another concept where your carbon becomes sort of a chiral. Now, what happens if you look the stereochemistry? What it can happen? First, you will say that how it will be suprafacial. Yeah, what are the options you can write on? One, I can say I can write suprafacial. Okay, keeping in mind now my chiral carbon, okay, can be in retention. One, it should be in retention. One option is there. Okay, I can say suprafacial retention. Can you draw that? Because it is a 1,5 hydrogen shift. Can you draw this? 1,5 hydrogen, just okay, sorry. A, and then you get a B, then you get a B, then you have your C. Okay. Just try to draw this suprafacial retention, because I want to see. Just I will come back, I will take a new paper. You guys try it. What are the things you can draw? See, I have a D. Suprafacial retention. Write your A, B, because it has been shifted from here. Then you write your C here, D. Now make sure that your carbon which you are writing okay, this is what now your carbon has been having the same configuration, that is retention. So another option can I write suprafacial inversion. Okay, you can think about suprafacial inversion can also happen. No, we are just saying that what are the possible options can be. Right, I can have an inversion. Then what we can think about? So I have a suprafacial retention, suprafacial inversion, and then I can write anyone. I can write intrafacial, yeah, very good. You can write intrafacial retention. Okay. So intrafacial retention will be just in the down, right, with the carbon. So C and D will be up and your methyl will be in the down. Okay. And then you can write your intrafacial inversion. See, once it comes to a carbon which is type of which is a chiral, then you have to think about these four possibilities. So one, it can be suprafacial retention, suprafacial inversion, intrafacial retention, and intrafacial inversion. See, most of the time, okay, if you do, you get suprafacial retention. When it is suprafacial, most of the time it will be retention. Okay. If it is an intrafacial, then it will be inversion. Okay. The suprafacial inversion and intrafacial retention more or less are same. So you have cases where you can get suprafacial inversion. These cases, this comes only in one case. If you take the rule, most of the time you will end up with suprafacial. If it is suprafacial, it will be retention. If it is intrafacial, it will be inversion. Clear? Now what we will do, we just take that Woodward-Hoffmann rule which we wrote earlier for methyl shift. That is 4n plus 2 heating H. What we said? We said initially it will be intrafacial, okay, then it will be suprafacial, then suprafacial, intrafacial. So what we found out, if it is a carbon with a chiral, if it is intrafacial, it should be inversion, right. So, I can put A plus I. If it is suprafacial, it should be retention, because it is suprafacial, there will be no change in your chirality. So, it will be S plus R. Fine. Now, I just add one term into your carbon shift. If it is just a methyl shift, no need to worry, it will be similar to your hydrogen shift. But if your carbon is a type chiral, then you have to understand whether it is an inversion or it is a retention. Fine. So, the rule can be done like this. For 4n, it will be A plus I or S plus R, 4n plus 2 S plus R or A plus I. Clear? Any doubt here? Okay. See, as we said in hydrogen shift, for 1,3 hydrogen shift, when you heat it, there is an exception that it does not undergo any reaction. Okay. Same way for carbon. Okay. For 1,3 heating, it does not follow this rule, whatever rule we are written. So, we will just see what it happens in that case. For example, I take our 1,3, just sigmatropic carbon shift, just taking 1,3. Okay. For example, just we will take the methyl for simple representation, you will understand later why it. So, it is a 1,3 shift. You know it goes by allylic cation, as I earlier said. If I break this, okay. Shall we draw the HOMO of this? Because I am doing in heating. So, I am just considering the HOMO of allylic cation. So, how the HOMO looks? It should be just the opposite, right? Lobes. Now, I have to put my carbon. Sorry, I have to put this. Now, you have your. Okay, I will just put your carbon here. Fine. Okay. Now, you know that this is not going to happen. Fine. So, what the rule says? So, it will be intrafacial inversion, right. See, according to rule, it should make an intrafacial inversion. Yeah, looks like to be, because it says it can be, but this methyl is so nice. Instead of doing this big thing, what it does, it simply invert itself here. If you just see this, how it is easy for this guy to do this. So, it is so nice to see how these guys work. See what it did, it's just inverted itself. Okay. Now, it can do easily suprafacial, right. Why it has to do now intrafacial? Because the orbital is favored. See, actually by rule it should go intrafacial inversion, right. But what happened in this case? You get suprafacial inversion. So, this is the only one case I think you get suprafacial inversion. Most of the case if you say you will be dealing with suprafacial retention and intrafacial inversion, yeah, because intrafacial may you get inversion, suprafacial it maintains. So, this is the only case where you get suprafacial inversion. So, keep that in mind.
But in the case of methyl, the carbon is not guided. So, there is no question of
yeah, see I am just taking for an example simpler. If it is x, y, z it will be clear, but we are not seeing the difference because, but actually it happens suprafacially inversion, you are not, it happens like that, you are not observing by the product.
But because if so, it is not methyl, but instead of methyl,
yeah, if you have a chiral carbon definitely you can observe, it will do suprafacial inversion and you can clearly observe that from the product.
So, this is only for 1,3 sigmatropic.
Yeah, it is only for 1,3 sigmatropic shift, that also particularly in heating. So, this heating 1,3 heating in both the case hydrogen as well as carbon does not fit exactly with your rule. Okay. That only point you have to remember. Clear? Any doubt with this? No. So, shall we get into problems? So, we will do some problems on 1N sigmatropic shift. You can say examples or I say problems. So, when you write this, the stereochemistry is very important, because you are going to talk about so I have a system like this. Okay. Just I am going to photolyze. So, now first thing you have to find out whether what shift it is. Okay. The second thing you have to find out the stereochemistry, right, because I am defining my hydrogen. So, what shift you are going to, because it is photolysis, I have defined the condition. So, H mu which is possible 1,3, H mu 1,3 is very fast. Okay. See 1,5 heating matter 1,7 again H mu, because these are all orbitally favored one. So, you can do then 1,3 hydrogen shift. The second question is that whether it will be intrafacial or suprafacial. So, what the rule says? What system it is? It is 4N. So, light it is S, right, suprafacial. So, first you write that, then write the product once you finish it. So, it is 1, 2, 3, right. So, your hydrogen will be same phase. Okay. Simple example, but tells you what happens. Clear? Okay. A system like this. Now, I am saying that I am going to heat it. What you can think of heating the system? see you have an option, if you count you have 1 3 and you have 1 5, that is all. So, it should be 1 3 or 1 5 and I am giving heating, you are just think which is orbitally favored, your 1 5 is favored. Okay. So, it undergoes a nice 1 5 hydrogen shift. So, 1 5 heating, what it is, intra or supra? Suprafacial. Just keep that formula into your mind. So, then I can write the numbers 1 2 3 4 5, right. So, it is a suprafacial right, you can get this. Any doubt? Again you can, if you heat this, what happen? I can again heat this, again you will end up same 1 5 hydrogen shift, but not the same product, but same chemistry, 1 5 hydrogen shift suprafacially, write the product. Number it and write the product 1 see 2 3 4 5, right. My hydrogen can come here. Very good examples to work on. Yeah.
Isn't there any chance of deuterium movement?
Which movement?
Deuterium D.
Deuterium, no, hydrogen moves very fast comparatively. That's good. Yeah, deuterium also can move. Okay, so we don't need to go by one by examples. Okay, we'll just change. Otherwise, it looks like easy to find out. So, now I heat this. What do you look for? See, the hydrogen OAC are one side, okay, deuterium and hydrogen on other sides. So, this is OACs, O acetyl. Hydrogen, this is your hydrogen, deuterium, OAC and hydrogen. So, what you observe? Now, I heat this guy. Or if I photolyze, whatever, if we did just heat it, what you can think about? There is no hydrogen, you are thinking about hydrogen shift. Yeah, you can think about your carbon shift, na? 1, 2, 3. Okay, this carbon can shift, na? So, it will be 1 3 carbon shift. So, what it is? What the rule says? It will be an inversion, right? So, can you write it? So, it should be inversion, keep that in mind. So, if I will be happy if you write the structure before me, because it will be, I want to know how you see this particular carbon when it moves, because it is undergoing a inversion. So, I know that you will write this part, okay, but I will be much interested to see how you write this. Okay. So, you have a OAC this side, okay, and you have an hydrogen here, that is fine, because it says same like that. What happened this side now? What will happen to this hydrogen and deuterium? It will be other way around, because you are inverting, right. So, now you can write your deuterium here and you can write your hydrogen. See, that is how you should know, because this inversion and retention is very big in writing the stereochemistry. It is not only about hydrogen shift or methyl shift or 1,3 or 1,5 or 1,7, it should be with your stereochemistry. Fine. Any doubt? Take another good example here. See whether you guys can write this, the same one, but OAC. Okay. Just I am taking the same example, just want to see again how you write this, the way different way I am. Is it just the same one, right? See, that is what I am saying, the way of projection, it is the same example, the way of projection is like this. Okay. So, do not think like when it is projected you see that this is the different example, okay. It is the same example, that is what I want to know. So, when you write you can open up this and then also you can draw your stereochemistry. Okay. Same way for this product, if you write in another way, see I am just, it is, can say it is 3, the same way I am writing it. Now, whichever way you like, you can open it up and I am seeing people writing like this also, it is also good way of representation, right. Same example, different way of writing it up, the same compound. So, you should know the many ways of seeing the molecules, that is why I just want to write this one, fine. Okay. Now, we will take one good example, which is your test for Woodward-Hoffmann. See, you take this example, okay. If you heat this, for example, what you should get? I take this example and I heat it. So, it is 1,5, right, because it is very clearly says it is 1,5. 1,5 heating is what? Suprafacial, right? Yeah. So, can you draw the structure? So, it's simple. So, it is suprafacial. So, get a hydrogen. So, it should be what if I number it R, this is R, Z and E, right. Okay. See what happens in this compound, once you do the heating I get another product which is S, Z and Z also along with this. So, I get RZE, I am getting SZZ, that means I am getting different stereochemistry, right, stereoisomer. So, how it is possible? Any idea? 6-membered. Now, if I just eat, I get RZ, that is, you say it is 1,5 hydrogen shift with a suprafacial. Are you thinking, for getting this, are you thinking like intrafacial? But intrafacial never happens in 1,5. Yeah. So, what happens there? What happened to this molecule? If you take in solution this molecule, see this molecule does very nice CC bond rotation, single bond rotation, right. So, you this is get methyl and deuterium. Yeah. You can have other way around. So, it can do a CC bond rotation, that is possible, right. And this in 1,5 undergoes 1,5 hydrogen shift suprafacially, it will give you the other product, which is SZE, that is what. See the nice way of writing it. So, these are all things you should know. Okay. And taking one molecule, so it undergoes a CC bond rotation, so it can give this. And these are all the options which you have to open when you do this type of examples. So, suddenly do not break the rule and say, no sir, it might also go inversion, so I will get this product. Okay. It does not happen that. We will take another molecule. This molecule you have to save, because where you have studied this molecule in lot of places. Any idea where you are? Oh, sorry, you have a methyl there. 1, 2, methyl here. You have a methyl there. Okay. You have studied this synthesis. Where it studied? It does. Then it does a electrocyclic ring closure. You end up in sort of a vitamin. Vitamin D. You study this in vitamin D synthesis, right. What shift you study there? See this, if I do a photolysis, see when people ask, they ask like this only, okay. Photolysis, what do you expect? This cis trans and sigmatropic, any sigmatropic reactions? Any sigmatropic, that we are dealing with sigmatropic only. We are dealing with right now with hydrogen shift or methyl shift. Anything comes in your mind? See, if I write this hydrogen, then suddenly things comes to your mind. If I write hydrogen like this, what happens? 1,7. See, if I don't write that hydrogen, then you have to think. Yeah, see, if you have methyl, just please write the hydrogens, then it is easy to find out. Yeah, it will be nice 1,7 shift. Okay, you can write 1, 2, 3, 4, 5, 6, 7. Yeah. Then nice 17 hydrogen shift. So, what is that, antifacial or suprafacial? That is very important. So, 17 hydrogen shift. So, what your rule says? Suprafacial 17. One seven is what? One seven is what system? What electron system? 4n system. Yeah. Heating me. Yes, just because this geometry is little bit unfavored for suprafacial, it should be let's check it up. I will get back to this regarding the configuration. Because this geometry is little bit favored, looks like to be an antifacial. Okay, looks to be antifacial geometry. I will get back to you in explanation. Okay. Okay. Okay, I have a system like this now. So, now I say that I need other way around. I say that this chemistry goes suprafacially retention. Okay. What it says? I am saying that suprafacially double bond. Oh, example 5. Okay, sorry. Yeah, sure. We need a double bond because you shift this, you shift that. Yeah, right? So, I want this reaction. This reaction goes by suprafacial retention. Okay. So, tell me what condition it is, other way around. This is suprafacial retention, this geometry. So, what condition shall I use? Because first you find out what shift it will be. What shift you want to do? 1, 2, 3, 4, 5, right. So, I can move this carbon. So, it will be 1 5 shift. So, 1 5 if I want suprafacial retention, what I have to do? Heat it or I have to photolyze? Heat it. See, that is other way of finding out. Okay. See, one way I can ask you that heat, what you get. Other way I can ask you that this is the geometry I got. So, find out the condition. Okay. You should do other way around also. So, on heating, now you just draw the structure. So, it should be a methyl here. Okay. So, further also you can do this same way. Then what you get? Again same, right. Any doubt with these systems now? So, you can do any examples then. Huh? Okay. Now, I will give you one example which you guys to try to do. I have a system like this. Okay. I have many combinations here. So, I say that I am just stipulating it for heating. What you want to do? Heating. So, 1 5 what 1 5 there are two choice, methyl or hydrogen. I can push my methyl, I can push my hydrogen. What you want to do? Yeah, 1 5 hydrogen shift. Very good. So, 1 2 3 4 5. So, now you know how it is. Right, you have your hydrogen here. So, now you have a conditions. So, you see if an example is given, you have to find out the condition. Okay. If the condition is known, then you find out whether it is 1 5, 1 3, 1 7. Then you find out whether it is suprafacial or intrafacial. Then you find out whether it is a retention or inversion. Any doubt with these examples? Okay. So we will stop your 1n hydrogen shift. That's all on 1n hydrogen shift. So we will be then concentrating on NM sigmatropic reactions. Clear?